This is a preview of lecture number 3 in the Einstein Maths program for high achieving learners. So in this preview, we shall give you some hints and ideas on how to tackle some of the problems coming up in the lecture proper. Try and see if you can use these ideas to help you make progress in these for grades 4 and 5. So we're going to start off by discussing networks. We'll give you an idea of what networks mean. Of course, there are many networks that are in use these days, especially traffic networks, networks involving airlines, planes, and how they travel. And the examples that we are choosing are very similar. The first problem that we are going to pose is the well-known traveling salesman problem. This problem is an unsolved problem to date. Nobody knows a solution that works for all cases. Nevertheless, we shall take a simple version of the problem to understand it. So in our version, what we have here is a salesman. He lives in A town. So let's say that's A town there, the orange. And he wants to visit all his customers staying in towns B, C, D, E, and F. The distance between each pair of towns is shown on the diagram. So the distance there is 10, there's 24 between B and C, it's 8 there between C and D, and so on. Question: what is the shortest possible route he can follow? Remember, he must come back home, must come home at the end. He can't go out there and stay somewhere permanently. All right, I think that makes sense. Nevertheless, we must say it. So now, if he starts sort of at A, let's suppose he goes to E, he goes to C, he goes to D, he goes to, he comes back to A, goes to C, to B, to A, to F, and back to F, and back to A. So that's a very long route. Is there a better way to do this? That was very long, you see, so that takes us 14 plus 8 is 22, plus 12, plus 13 is 35, plus 8 is 41. Come back, that's 49. Go back to 10. Oh, it's getting very long. Now, can you find a route that should be followed which will help the salesman to cover all his clients, come back to his hometown, but cover the shortest possible distance? So can you add up the distances each time and see what's the best possible route you can come up with? Okay, so you can try, experiment with many different options. Up there, up here, up there, down there, down there, down there. You have to go to the full town. You can't change halfway. There, that covers all. Okay? Except that I did one twice. So that's one possibility, but I'll leave you to try out different combinations to see how far you can go with that problem. The second one is a problem involving water engineering. Again, it's very similar. This time, however, according to the problem, in the map below, a water pipe is to be laid so that every town gets a supply of water. If the pipe starts at A, so there's a pipe starting here, what is the shortest path that will take water to every town? So if you start here and you go up, there, down here, H, G, I, E, F, it doesn't seem, it's not a clear path. Let's try it again. Trial and error, you see. And then we're going to add these up. Remember, it's not necessary to come home again. No need to come back to A. No need to come back to A. Right. If you start at A, you can follow a route that goes like that, like that, like that, like that, if you want. Okay, down there, 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 there. Which one is missing out here? That route worked. If you go like that, there, and there. That covers all possible towns that will get the water. Now, how long is that route? That's 90 plus 70 is 160, plus 50 is 210, plus 130 is 340, plus 100 is 440, plus 80 is 520, plus 50 570 plus 110, that's 680, plus 100 to get to I, that's 780. 780 kilometers. Can you beat this? Can you beat this with a better route? I'll leave you to think about that. Okay. In the meantime, we go to another one, traffic engineering. Very similar problem. Cars enter this town. This is the map of a town. Cars come in at X and they leave at Y. Right? And they can follow any route here to get to Y. What is the shortest route a car can follow to go through this town? Okay, so again, you got to experiment and see how well you can do this. What's the best possible result you can get? You could probably go down here, there, up there, and out. What route is that? That's 8 plus 8 is 16 plus 6. 16 plus 6, 22, plus 4 is 26, plus 8 is 34, and 9 is 43, 45, 48. Can you beat this? Can you find a better path? All right, we shall see in the lecture proper if it's possible. Caretaker's a headache. Very same problem, similar idea. Caretaker of this park is about to sweep the park with his electric sweeper. No matter how hard he tries, he can never avoid sweeping some pathway twice. So he has to go some way twice. Can you help him find a path without going over a path twice? What is the shortest distance he can do to do his sweeping and come back to H? Again, you will need to find a path that he can follow without having to go past the same one twice. Leave that for you to tangle with, right? Finally, a game. Try this game out with your friends. If you take 6 dots, right? If you take 6 dots, this is for 5 dots. If you take 6 dots, 1, 2, 3, 4, 5, 6, and you're allowed to join the dots with the red or blue lines. Right? Let's say it's a game. So your first player takes a turn, he uses the red line, purple. The next person has to go, he chooses orange, and join any 2 dots, and you carry on like this. The first person to make a triangle of the same color, for example, like that, is the one who will be the winner. Well, the first rule says that the loser is the first person to complete a triangle. Then in the second iteration, I completely changed the rule and said, play again this game. And then this time, the winner is the one who makes a triangle with the same color. Try this out and see if you can get it to work. And the question here is that, is it possible for this game not to have a winner? Can it be a stalemate? Well, we shall discuss this proper in the lecture number 3. See you guys then.